My name is Gabriela Aleksić, and my part of the talk will explain reasons and actions behind this research. And in the second part, my colleague Tomislav Cigula will present some details of it. The research introduces a model for the evaluation of the paper-based materials used in making preservation enclosures for various library material. The aim of this research was to provide an insight into the importance of choosing the appropriate materials that can fit the needs of an individual object as well as the entire collections. Since the subject is also relating to several aspects of conservation of library material, the results were meant to provide information useful to both conservators and other experts in the field. One of the most effective methods of preserving the objects is their encasement. Preservation enclosures aim to improve storage conditions and handling operations and are a protection from different threats that come from the environment. They're also known to minimize damage and damage to the objects in disaster situations. Fragile and valuable library material especially benefit from the encasement as it is properly supported and kept in one place. Phased conservation is also based on making a custom protective enclosure to improve storage conditions, handling operations, and to avoid unnecessary restoration treatment. The National and University Libraries in Zagreb is a large system. It is also a place of storage for various library material, such as manuscripts, books, newspapers, maps, atlases, drawings, microfilms, and etc. And they all require a different approach to their preservation. Protective enclosures in the storage systems of the National and University Library in Zagreb are mainly in-house made, as they present economical and efficient solution for preserving various library material. They come in many sizes, weight ranges, and shapes, and their design is based on standard references and common conservation practices. Preservation enclosures in the storage systems of the National and University Library in Zagreb include wrappers, folders, envelopes, sleeves, slipcases, portfolios, passepartouts, and boxes. Some of them are only meant to be used with other enclosures. Envelopes, folders, and sleeves are used to protect individual objects inside boxes, portfolios, or drawers. Preservation enclosures are made from paper-based materials, but can contain polyester films, book cloth, twill tape, etc. Since paper-based materials are prone to tear and wear, some enclosures are partially or fully covered with book cloth or covering paper in order to become more solid and provide appropriate protection for the object. Most often, only the spines of cardboard portfolios are reinforced with book cloth. In this research, 9 paper-based enclosure materials were investigated. They included 2 papers used for making sleeves and jackets, 1 covering paper, 2 cardstocks for making 3-sided folders and face boxes, and 2 cardboards for making boxes, portfolios, and passepartouts. They were selected on several bases. Some were evaluated and compared for the purpose of identifying the ones with better overall properties, and others have only been tested for the better understanding of their protective performance and the process of the evaluation as a whole. Storage enclosures are required to be thin and therefore space-saving and weight-minimizing. Space-consuming and heavier enclosures are usually suitable only for very fragile objects, and their construction is often time-consuming. In this research, materials from the same group were evaluated for the purpose of determining the properties in which a material of lower thickness and grammage thrives and presents a more appropriate choice. Protective enclosure should be safe for the object it contains or comes in contact with. It should also be free of topographic features and smooth as possible. Smoothness of the preservation material presents a valuable physical feature since it reduces the possibility of occurring mechanical damage to the object's surface during storage or handling. The smoothness of the materials, according to Bekk, was also assessed in this research. It is of great importance to choose enclosure materials that won't chemically damage the objects they come in contact with. Since acidity is very degradative for the paper-based materials, it is required that enclosures are made from acid-free materials of highest quality, as they present a long-term solution for preserving library material. Despite both being acid-free, sometimes it is difficult to choose whether to use a neutral or a buffered material. A buffered material with alkaline reserve will remain acid-free for a longer period of time and should have better properties than the neutral one to some extent. In this research, both neutral and buffered materials were investigated and the results had been compared. All papers age, and that causes loss of their value, strength, and surface properties. However, archival paper is known for its superior durability. When exposed to dry heat, materials become brittle and less resistant to mechanical stress, and even a small increase in moisture of the environment can significantly influence properties of those paper-based materials, as they will take up moisture from the environment in order to reach concentration equilibrium. The strength properties of the materials were monitored and examined under experimental conditions that are known to cause paper aging more rapidly, and the moisture content of the materials was also considered both before and after these tests. Mechanical damage to the objects occurs suddenly, most often when the object falls, scrapes against the other object or a surface. This can happen during the handling, transport, or an earthquake. Good strength properties of both enclosures and enclosure materials are especially important in the context of unexpected events such as disasters, as they protect the objects from abrasion and compression. In this experiment, 4 types of strength properties of the materials were evaluated: the tensile strength, the folding endurance, the puncture strength, and the bursting strength. One of the most common threats for the collections is the water event. Water outbreak can be a result of different factors, such as plumbing and roof leaks, water pipe breaks, natural disasters, and fire extinguishing, which can all cause serious damage to the library material. The extent of the exposure to the water can significantly vary and affect library material differently. As a result, it may become soaked, wet, or damp. In this research, different degrees of exposure to water were examined by determining the water absorptiveness and the water wettability of the materials. The quality of the materials also depends on their efficiency to act as a barrier. The most widely expected barrier properties are a resistance to water vapor, air, odor, gases, grease, and oil. Good barrier properties are also highly important for the enclosure materials, and water vapor presents one of the most common risk factors for the library objects during the water event. One of the objectives of this work was to investigate to what extent are different enclosure materials permeable to water vapor, and to what extent are some materials more impermeable compared to the others. The experiments were conducted with standardized tests in order to analyze and evaluate smoothness, strength properties, water resistance, water vapor barrier property of enclosure material. They were also subjected to additional non-standardized tests in order to assess the extent to which their strength properties change after the exposure to the factors known to cause paper aging more rapidly. An evaluation and the comparison of the materials were made for the purpose of identifying the ones that meet multiple requirements. The decision to use a certain material, whether in making a custom enclosure or a non-custom one, should be based on thorough knowledge of the materials to be used, along with other relevant criteria. However, determining enclosure materials quality doesn't say much of the preservation enclosure performance itself. Many factors, including how it's made and whether it's positioned and stacked on the shelf properly, like that in the picture, will determine the final result. And this brings us to the end of the part 1. My colleague Tomislav Cigula and I decided to split our talk into 2 parts, and his part comes next and will include details of our research, so please stay tuned. Thank you for your attention, and I'm looking forward to hear from you in the Q&A part of the session. Tomislav, the floor is yours.
Okay, so as the moderator said, I'm Tomislav Cigula, assistant professor at Faculty of Graphic Arts at the University of Zagreb. I'm head of the department for graphic materials and printing plates. And my primary research is in the field of material characterization and optimization for printing and reproduction processes. I'm new to the field of preservation and of cultural heritage or books, older books. My primary goal till now was how to make a print which will be very attractive to the customers and try to maybe put them into buying options. I will make this second part of the presentation where I will touch a bit more on the methods which we used and show some results. So hopefully it will be very interesting for you. I want to just say that although we simulated some possible occurrences which could happen, like high humidity or dry air, which are part of the possible processes of floods or fire, we did not simulate direct soaking of the material in water or expose it to direct flame. So you will see what was the idea behind the research. So first, we wanted to see which methods are more significant for material characterization. As you most probably know, that paper and paper-like materials have a lot of measurement methods which could characterize its properties. And we wanted to really set up some system in which we could use less methods, but gain proper results. The second one was to indicate, based on these methods and the results of the characterization, which material is suitable for use in its primary purpose. And in the end, the idea was to see the crisis risks. So how can we preserve the materials if some kind of crisis which we are experiencing every day can damage or indicate what will happen to the material which should be preserved. The evaluation of the materials were, as said before, made by numerous research methods, but I will here present or in detail explain just a few of them due to the less time which we have in this presentation. So as you most probably know, the paper and paper-like materials are often very rough surfacely, and this can be challenging in terms of printing, but it also challenging when you try to preserve some collection due to the possibility of rough surface damaging the surface of the collection, printed one or unprinted. On the image left, you can see the micrograph of paper surface, the fibers, and it's on the small upper left, you can see the how this surface comes very roughly. On the right side, it's a unit which enables evaluating smoothness of the sample by Bekk test. The Bekk test really is commonly used in paper characterization, and it's a relatively simple method, gives the value in seconds. When I first tried it, it was very for me, it was very strange how to get the smoothness in seconds, but it's really the time in which air goes through the pores of the paper surface and fills some container. And as larger the number, that means that the paper is more smooth. Secondly, used evaluation methods were more tended to the mechanical part of the paper. For once, it was the folding endurance. This is something we have to think about when we are using materials which are meant to the wrap of a collection. And although this material could be changed. So, for example, when we open some collection and folded the material which it was wrapped, we can change it if we see some breakage, but that means that we will use more material. And the idea behind was that we can choose the material which will enable longer usage. This unit on the left, you can see, so you put the sample in between the clamps, and the folding endurance tester really folds it back and forward and counts the number of these folds. So we can determine which material will be more resilient to breakage from the folding. On the right, you can see the Mullen bursting test. As you could already see in Gabriela's presentation, the samples there were presented. So the idea behind the bursting test is just to see how the material is coping against pressure when something will fall or when something will try to damage. So this is really a very helpful feature of the material, which could tell us what will happen when we, for example, if something falls onto the collection or collection itself falls down. Besides the material mechanical properties, we also wanted to see the barrier properties like the water vapor transmission, or how it will get wettability. This is the surface feature of the paper, and as you can imagine, they play a really significant role in preservation. The paper and paper-like materials are losing its properties when exposed to high humidity, and these two methods will give us the answer how some preservation material will be in terms of water, when water will come into the contact. So we wanted just to see water wettability. In future, maybe we'll try also the oil wettability, just to determine how the material will be behaving in those occurrences. The wettability with the goniometer is really determined by observing the shape of the liquid drop when it comes to the contact with the paper. Really, this is the topic which is very important in the significant science fields of various industries. For example, this is also in air industry very important, where you can, when super hydrophobic surfaces are most common, and just to build its usage even in space. The water vapor transmission really determines the barrier properties of the material when there are different humidity in the surroundings. This method which we used is built like when we get the water in some units, and there is a humidity of 100%, and we just weigh the sample and measure how much water vapor has evaporated through the sample into the surrounding in some time. The methods which were also conducted, but I really don't have a lot of time just to stress them, is the puncture test, strength test, the tensile strength test, and water absorptiveness. So this will be more present in some future papers which will be showed. Just to get the insight of this research, we wanted to show you some results. So on the image on the left, you can see the change of the bursting strength due to the surroundings humidity change. The blue column is when we put the material into the dryer and dried it out, so it didn't had any more moisture inside. The orange column is when we expose this material to the environment in which 100% humidity, relative humidity was, and we put it in 48 hours. And the gray column is when the material was stored in perfect conditions, 50% of relative humidity and 20 degrees Celsius. As you can see, both high or low humidity in the surroundings causes decrease of the bursting strength. But we can also see that the bursting strength of material which is exposed to the high humidity is higher. On the right side, you can see the water vapor transmission rate when we tried out the materials with different thicknesses. So the less thick material were on the left, and the very high thickness of materials were on the right. And one would expect that more thick material will have higher barrier properties, but as you can see, the first 5 results, although the thicknesses are rising, the water vapor transmission is even higher. When you put really thick materials like MQ1 and others, you get the lower transmission rates, but there is also not regularity that the higher thickness will result with better barrier properties. So to conclude this presentation of the research, we can say that proposed methods could be used in characterization of preservation materials, and furthermore, it enables their comparison. Secondly, which we can get from this research was that it showed that materials do not react to higher temperature or high humidity equally, and therefore these characterizations could help us in material selection. So with this slide, I'm really coming to the end of my presentations. If you have any need for further information, now you will be able to ask us in Q&A, or you can contact us on these contacts emails from my colleague Gabriela and me. Thank you for your attention.